Okay, today's topic is multiple token recognizers. So now we're going to get practical. Up until now we've been a little bit theoretical, but now we're going to get practical. We're going to see how to actually use these finite state machines to help us do our translation project. And if we have time, I hope to have a little demo here so we can actually start doing a little coding with these finite state machines. So, the first thing we have to understand about a multiple token recognizers is what is a token? Now this is all translation terminology. So a token is a string of terminal characters that has meaning as a group. Now let me illustrate this for you by an example. You know that your translator, what it's going to have to do is it's going to have to translate from what language to what language? Your translator. You're going to write an assembler. That translates from what to what?
Assembly language.
Assembly language to machine code, to hexadecimal machine code. That's what your program is going to do. So let's suppose that you're translating a program, and the program has an assembly language statement like this. Suppose it has like main load word accumulator 0x000a comma immediate. All right? Is everybody with me on this? Okay? And actually, somewhere else down below in the program, you might have something like this. You might have load word, so let's just do ... You might have load word accumulator 13, comma, immediate. Right? So what your translation program has to do is it has to scan these characters one at a time. Sounds like that's what a finite state machine does. It scans the characters one at a time. So your translation program is going to be scanning these characters. All right? Now, so the first thing is, what's the definition of a token? A string of terminals that have meaning as a group. So let me show you. First of all, let me show you what is not a token. So, let's just state this. WA space, so the string WA space 0x0, is that a token or is that not a token? It is a string of terminal characters in our source line, but does this string have meaning as a group? No. Why not? Because what is it? It's the what? It's the tail end of a what? Yeah, an instruction mnemonic, right? And then it's just the what? The first part of this. So this string is not a token. You see what we're saying? Because the token is a string of terminals in your code that you're trying to translate, but it has to have meaning as a group. So tell me, let's do another example. What is a token? What would a token be? What's an example of a token? Yeah, or up here, like up here. What would the tokens? If you were to group these, the ones that have meanings as a group, what would they be? What would the tokens be? One of them would be what? Main colon, because that's a what? What is the meaning of what is main colon in assembly language? It is a what? Starts with an S. It's a symbol. All right. And what about LDWA? That's a token. Because that has meaning as a group. Because what is the LDWA? That's an instruction mnemonic. Does everybody see? So the string, this is not token, but the string, let's just say, here's another token, 0x000a. The string 0x000a is a token. So does everybody see what a token is? Yeah.
Is just I a token?
That's a good question. And the answer is it could be. I think that's a reasonable definition of a token. Or what you could do is you could combine the comma and the I to be a token. So in a sense, it's a little subjective, and it's up to the programmer to decide what the tokens are. So you might group, and for example, you could call main a token, and you could call colon a token. Main could be an identifier, and that could be, you see. So there's a little, there's a little gray area as to what you consider token. But we definitely know that WA space 0x0 is definitely not a token, because that doesn't have meaning as a group. Yeah, so that was a good question. All right. So that's the meaning of a token, and the first stage of your translation program is going to be to recognize the tokens in a line of assembly language code. And that process is sometimes called tokenization. Sometimes it's called a tokenizer. We'll get to this terminology later. One word is lexical analyzer, and another word is tokenizer. So those are two words that mean the same thing. And what both of those words mean is it's the process of going through the source code and recognizing the tokens. You know, figuring out the symbols that have meaning the strings that have meaning as a group. All right. Now, what's this topic? Multiple token recognizers. Now watch this. Suppose that you're here. Suppose that you just scanned this LDWA and you figured out that that's a token. And then what's coming up, and what do you know should come up next? I mean, what could come up next after this token? What could come up next? 0x000a. That's what could come up next, right? But there's another possibility. What else could come up next? Instead of 0x000, what could come next? 13 could come up next. So how do you know ahead of time when you're trying to recognize these tokens what's coming up next? So what your finite state machine has to do is it has to be able to recognize either this or this. You see? Because it doesn't know what's coming up next. Is everybody clear on this? See? So because you want to recognize tokens, well, I mean, because you don't know ahead of time what the programmer has, the source code, and in fact you're trying to figure out, you're trying to tokenize, you're trying to discover the tokens, but the thing of it is that you don't know ahead of time which one to look for. So what you have to do is you have to look for many at the same time. You have to look for, so that's what a multiple tokenizer, that's why we need multiple token recognizers. So a multiple token recognizer is a finite state machine with multiple final states. And the final states determine the token that is recognized. Now let's work through an example that's based on this idea of recognizing either this or this. Now watch how this works, you guys. So here's in figure 7.22. Now let's look at part A of the figure and the top part of that figure. Now, do you see that the top part of figure A is a finite state machine that would recognize what on the board here?
That's about the top.
Yeah, it would recognize, you notice the start state is A, it would scan this 0 and go to B, and then what it would do? Then what would it do? It'd scan either the what? Uppercase or lowercase x, so it would scan that and go to state what? C. And then it would do what? Scan this hex digit 0 and go to state what? D. And then do what? D, D, D. And then when we got to here, we would see that there's not a transition from that state on a comma, and therefore we would, and so that would be the end of that finite state machine's job, and that machine would have recognized a what? This token, 0x000a. Now does everybody see how that worked? All right. And furthermore, what about the second machine down at in part A? What about the second machine? What does it recognize? What would it recognize? This 1 and then this 3, right? So the 1 would take us from state E to state F, and then the 3 would take us from state F again to state F, and then we'd have a comma, and we'd say, oh, that comma means that we don't have a transition on that comma, so therefore we have recognized this 1, 3. So now here we have two separate machines, each one of which recognizes a different token. But how do we build a finite state machine that will recognize either this or this.
Do that one.
Well, yeah, now you're doing an implementation with the program. You're saying if, well, no, I'm saying, what about how do we do it with a finite state machine?
It's non-deterministic.
Yeah, and how can we put these, the question is, how do we put these together to make one finite state machine that would recognize either? What would you do?
The first starting.
Have a new start state, and connect, and then have a transition from that new start state to where on what?
Like here.
It's like to A or E.
To A on what transition?
An empty string.
On the empty transition. Now, do you see in part B of the figure how that works?
Why?
Now you see this finite state machine will recognize either this or this. And now there's two final states, and if you wind up in the final state in the top one, it has recognized this, and if you wind up in the final state in the bottom branch, it will recognize this. But now this is a multiple token recognizer. Yeah.
But why did you even have to do an empty? Why couldn't you just go G to B on 0?
Ah, very good. So now that's the next step. So now how do we eliminate empty transitions? Good observation. So here we have an empty transition from G to A. So we have a transition from G to A on the empty transition, and then from A to B on 0. So what was our rule? You go from where to where?
From G to B.
From G to B on what?
0.
On 0. And then you'd also do what? Go from G to F on what?
1.
On 1.9. Question?
Yeah, so is each finite state machine its own program, or is it one program with multiple?
It's one program with multiple tokens with one, and we will do the implementation. You'll see the implementation a little bit later.
Okay.
Yeah, for right now we're just doing the finite state machine design. Okay, so look, so as you anticipated here in figure 7.23a, we can eliminate the empty transitions by going from G to B on 0 and going from G to F on 1.9. But now what do we do? Now what do we notice? States A and E are what? Inaccessible. So what can we do with those? Remove them. So boom. So there's our multiple token recognizer. Now see how you use finite state machines to build tokenizers, to build recognizers. Does everybody see how that works? And so now, you can tell what the state that you end in. So now we have multiple final states, and the state that you can tell by the state that you end in what token you have recognized. And so what you're going to do is your translation program is going to implement a big multiple token recognizer, and it's going to have these different final states, and you can tell in your code by what state you end up in what you have recognized. So you see how practical this is, how these finite state machines. I'm telling you guys, finite state machines, all of computation is based on finite state machines. When you guys take automata theory, Turing machines, and even if you take the computer organization class where we do this in hardware what we do is we construct finite state machines with chips, with computer chips. We build them and we cycle through them and test them at the hardware level. So these finite state machines, they are pervasive. They happen here in software and these translation things, and they also happen in the hardware. And so what happens is, in fact, your computer is one great big gigantic finite state machine. Yeah, and that's what it's doing as it cycles through the von Neumann cycle. It's a big finite state machine. Anyway, at the hardware level, but we are applying this at the software level. Okay, now, so here in figure 7.24, here's another example of a multiple token recognizer. Now, can you tell from figure 7.24 what two tokens it recognizes? What two things would it recognize? What two things does it recognize?
Strings of letters.
Or a letter or digits.
Or yeah, it looks like it's an identifier that starts with a letter and can have either a letter or a digit, or it can be that followed by a what? A colon. Okay, so now how would this? So this finite state machine is going to be part of your big finite state machine in your translation program. So now let's take a look with these examples. If we had this finite state machine running and we were at this point right here, what would it recognize? L, on L it would go from what? From A to B, and then the D would stay on B, stay on B, stay on B, and boom, now we're at the end with this space. And so what state would we be in? We'd be in state B. And so what would we have recognized? An identifier without a colon. On the other hand, if we are here and it's main colon, then what will happen is, what this will recognize is M will take us to state B, and then A will keep us in B, I will keep us in B, N will keep us in B. But then what will happen? The colon will take us to what? To C. And then we have a space after that, so we know we're done. But now because we wound up in state C, what have we detected? Not just an identifier like this, but a what? Well, no. What is this whole thing? Main colon? That's, well, it is a token. They're all tokens. It's a symbol. This is the definition. This is how you define a symbol in your programming language, in the assembly language. You see what I'm saying? So here, now we've defined, now this is how you would detect, this finite state machine would detect a symbol or this. Yeah? Does everybody see how this is going to work? We're thinking ahead about how, because you're going to be coding this up. Yeah.
So why isn't it necessary to have one that like recognizes like a space, for example?
Space is not a token. A space is not a, space is a separator. It's not a meaningful non-terminal in the language.
Okay.
Do you see what you see what we're saying?
Yeah.
And we're gonna have a very systematic way to take care of white space in your code, because you know in your code you can space them out however you want.
Okay.
Yeah. So that's the space. The separators between the tokens are not classified as tokens themselves. Okay. Does everybody see how these examples work and how these multiple token recognizers? Any questions? Okay. Now, a few more things before we actually take a look at an implementation. Now, what 3 ways are there to specify the syntax of a language? Grammars, finite state machines, and regular expressions. Now, here's something that you really need to know, that every computer science major knows, and this is just super basic. And that is, how do these 3 methods compare in power? In other words, which ones are powerful and which ones are more powerful and which ones are less? And the answer is, as shown here in figure 7.25, is that grammars are more powerful than either finite state machines or regular expressions. Now, what do we mean by more powerful? What do these 3 things do? What are they designed to do? They're designed to recognize valid what? Yeah, sentences in the language. They're designed. And the thing of it is that sometimes if the language is like an HOL6 language, and you were translating, with a compiler, then grammars are always required. You cannot use a finite state machine or a regular expression to translate an HOL6 language. Okay? And furthermore, you notice how we have in figure 7.25, you notice how we have finite state machines and regular expressions are at the same level? That is mathematically literal. When you take automata theory, what you will learn, what you will see, is that for every finite state machine there is an equivalent what? What do you suppose? A regular expression. And for every regular expression there is an equivalent what? Finite state machine. So they are equal in power. But each one of them is less powerful than a grammar. Okay, so that's a super important concept that you should understand. And let me try to give you an example of why that is. In a high-level language, you can say this. You can say I gets parentheses A plus B parentheses times parentheses parentheses C plus D times 5 parentheses, right? And then semicolon. This is, you understand, this is a valid statement in C, in the C programming language, right? And furthermore, in this programming language, in C, are there any, how much nesting do we have with the parentheses here? Just one. But here what do we have? This parentheses is nested inside this. And in C, what do you suppose the limit is? How deep can you nest parentheses? Is there a limit? There is none. Well, I mean, all machines are finite, and we can't have an infinite number of parentheses, but given enough memory, in the language itself, there's no upper limit. There's nothing in the language that says you can't have more than 10 parentheses nested deep. There's nothing that says that. You know, you could try it. Write a little C program and do do 50 parens, and then put a thing, and then do 50 parens, and then see if that compiles. It'll compile. All right? Now here's the thing. That unlimited nesting of parentheses is what a finite state machine and a regular expression cannot handle. You see? Because in a grammar, do you remember how we had here? Look at here, this expression. Let's go back to this expression. So here, let's go back to this grammar in figure 7.5. This is a grammar for an expression, right? And do you see that we had E produces E plus T, and then E produces T, and T produces T, concatenated with star, concatenated with F, and then T produces F, and then F produces what? Paren, E paren. But then the E can go back and do, and I think you had a homework assignment where you had, you did the syntax tree, and with a whole bunch of nested parens, right? Okay? Well, there's no way that you can design a finite state machine to do that, because every opening paren has to have a closed paren. How are you going to have them be equally matched? You see. All right. So that's why grammars. That's an example of an aspect of a grammar that can recognize a statement like this that a finite state machine cannot. All right, is everybody clear on that? One more big idea before we get to our implementation. And this is a really kind of a central idea in computer systems. Now, have you guys heard of the terminology a compiled language versus an interpreted language? Have you heard that before? What's the difference between compilation and interpretation? Okay, well here's the thing, you guys. Some programming languages are compiled. Other programming languages are interpreted. So both are common. And we need to understand what the difference is. And before we actually get to the difference, let me just give you the primary examples. All right, so first compiled. C and C++ are compiled languages. And interpreted, the biggest example of interpreted is Java. See, we're going to program in Java, so it's an interpreted language. So Java and PEP9 assembly language. PEP9 are what? Interpreted. So we need to understand what the difference is and what the trade-off is. So in figure 7.26, in part A of the figure, like we have on this slide, we have the compilation process. And now this is, when we talked about what a compiler does, this is basically just a repeat of what we've already done with C. So this is an example of how the C programming language works. So what happens is, you see in the top part of the figure, part A of the figure, the input is the source, which is written in a higher order language like C. And then the processing is the compiler, And what the compiler is that's a translator, and of course that translator has to be written in machine language. But what does it do? It converts the source program to what? The same program but written in what language? Machine language. And then that machine language program can come down and do what? Be in the processor. Are you with me? And then that program executes, and it takes the application input, and then while that program is processing, it takes that application input, processes it, and it produces the application output. So this is just review, right? This is what we've always known about what a translator does. And the fact that the processing has to always be executing in machine language. Now here's the difference between compilation and interpretation. In a language like Java, what happens is it is an interpreted language. So here's how it works. What happens is you write a Java program, and that is your source. Java is a HOL6 language, right? And then what happens is you invoke the Java compiler, but the Java compiler does not convert that Java program into machine language for the CPU. It does not. Instead, what it does is it translates it into what is called object bytecode. And this object bytecode is a universal, it's an intermediate code. And because it's not machine language, it doesn't get executed. So in order to run your Java program, you don't actually run the bytecode. What do you run? You run what is called the Java virtual machine. Does everybody see what we're saying? And what that Java, so you run another app. You actually have to, when you are executing a Java program, you're not actually executing that program. You are executing the Java virtual machine. You are executing a Java app that takes that Java bytecode together with the application input, and with those two together, it produces the application output. Now, in fact, look, do you guys remember, I think we've done a little, in the programming paradigms, we did a little Java programming on the command line. Do you remember what we, on the command line, do you remember what the command was to compile a Java program?
Was it like Java?
Java C. I think Java C, Java C is the Java compiler, right? So what you would say is you would say Java C, and you do, my source. All right, and this my source would be a mysource.java. I don't remember if you put the .java with Java C, or I might assume that it's, I don't remember, but anyway. And so this statement right here is what's on the top line of figure 7.26b. That's how you did this on the command line. But now look, what do you remember what file this produced? It was mysource.what? No, not a jar file. What did this call, when you compile a Java program? Do you guys remember in paradigms, or when we did this on the command line? Anything? Do you remember what did this produce? It produced what? It produced my source what?
Class.
Yes. .class. It produced my source .class. Now this .class is actually, that's bytecode. All right? So when you want to execute this on the command line, you don't execute see here, this is what we're executing, the compiler. Here, we don't execute my source like this. On the command line, you don't do this on the command line because that's not executable. Do you remember on the command line what we did? How to execute that? You'd have to say what? Java. Yeah, you say Java. So Java is what you're, so what is, when you execute Java, what are you executing? The virtual machine. And then what do you take as input? mysource.class. I don't remember if you I don't think you put .class, but anyway. On the command line. Does everybody see what we're saying? So that's interpreted. Now, what do you suppose are the trade-offs here? Which one, yeah, question, or what answer, or what do you think?
Like with the interpretation, you have to be running it through the machine.
Yeah, with the interpretation, you're not actually running the object code, you're running another program that then interprets that. So do you think that in terms of executing your app, is it faster or slower? It is always slower. And that's one of the big complaints that interpreted languages have, about interpreted languages, is it's always slower to execute. Because here, you see in part A of the figure, what you're doing is your program has been coded directly into machine language, and that your app is executing. So there's not an extra layer of interpretation during execution time. So, does everybody see that? So that's just one of the things you have to live with an interpreted language. But the benefit is that the software developers, the Java community, all they have to do is come up with one compiler that works for the Java virtual machine. So they don't have to have a different version of the compiler for all these different systems. So all they have to do is have a different version of the virtual machine, but that's a whole lot easier. They have to have a virtual machine for different operating systems and different CPUs. But that's a whole lot easier to maintain. See, so it's a software development thing. So, yeah. So does everybody see the difference between compilation and interpretation and what the trade-offs are? One more piece of information, some more terminology, and then we'll do a demo, and we're actually going to see we're going to code up, we'll implement a finite state machine in Java. All right, so in figure 7.27, stages of translation. Now here again, this is just super fundamental, and especially for our project, all translators, whether it's compilation or interpretation, whether you're compiling into bytecode or whether you're compiling into machine code, there's always these three parts to it, and they happen one after the other. All right. So, and the three parts of a translation of a program is, the first part is called the lexical analyzer. The second part is called the parser, and the third part is called the code generator. Okay? And your project will consist of these three stages. Okay? And so, by the way, we've done this, I've assigned this big translator project for many years now, and I have it all worked out with milestones. So it's not going to be all due at once at the end. So we're going to do, first we'll do the lexical analyzer, then we'll do the parser, then we'll do the code generation. So your project is going to be doing three stages that correspond to these three parts of the translation process. Okay? So let's just take a look at each one of these in turn. First, the lexical analyzer. The lexical analyzer is exactly what we did a few minutes ago with a multiple it's a tokenizer. So the lexical analyzer is also called a tokenizer. So what the lexical analyzer does is it goes and it tokenizes these. It breaks these up into groups of symbols that have, a string of symbols that have meaning as a group. So it does that. That's what the lexical analyzer does. It's also called a tokenizer. Then what happens is, now look at this. What is the input of the lexical analyzer? The source program. Now what is the output of the lexical analyzer? The output of the lexical analyzer is the input of a what? Of the what? Parser. So let's write this down. The output of lexical analyzer is the what? Well, first of all, what is it? What is the output of the lexical analyzer? What does it do? It recognizes tokens. So what do you suppose the output of the lexical analyzer? The input of the lexical analyzer is a stream of terminal characters. What do you suppose the output of the lexical analyzer is? A stream of what? Tokens. So the output of the lexical analyzer is a stream of tokens. Now this is just super, you got to get this concept. The program is going to be hundreds of lines long. You got to, if you don't have the overall concept, then it's not going to make any, we're going to get lost in the details. Okay? So the output of the lexical analyzer is a stream of tokens, and furthermore, and that stream of tokens is the what? To the what?
The input of the parser.
Is the input to the parser. Okay, let's just say which is a stream of tokens, comma, which is the input to the parser. So that's the key idea. And then what happens is the output of the parser is a list of intermediate code. All right? And the code generator takes that intermediate code and converts that to the object program, which in our case is what? Hexadecimal machine language. Okay? Output of parser is intermediate code, which is the what? Input to the code generator, which is input to the code generator. All right? So just keep that in mind. We'll come back to this again and again, and we just have to keep in mind that this is the way it is. Now, this figure 7.27, this is the way it's done for a compiler. This is, figure 7.27 is like with an HOL6 language. Okay, this is the way all HOL6 languages get translated. Okay, so that's just general overall. Okay. Oh. So here on this next slide, the input of the lexical analyzer is a stream of terminal characters. I didn't realize I had a slide for this coming up. So the input of the lexical analyzer is a stream of terminal characters. The output of the lexical analyzer and the input of the parser is a stream of tokens. And then the output of the parser and the input of the code generator is a syntax tree and or a program in a lower level language. That's what I meant by this. And then the output of the code generator is the object program. Okay? Actually, I think somebody asked the other day, do they actually do the syntax tree?
Yeah.
This is this is an example of a case where they might do that, where they might have the intermediate stage in between the parser and the code generator could be a syntax tree. Okay, now is everybody, so this is all just very basic translation principles. Okay, now finally, we're actually going to implement a finite state machine. Now, I think what I want to do now is, there's two different techniques for implementing a finite state machine. There's table lookup and direct code. And I think before we're going to start with table lookup. I think before I go through the slides here, let's do a demo. Okay, so here's our demo, and the program that we want to show is in figure 7.28. So here's the code for it. So here's the figure 7.28 project. Here's the source package. Here's in the source package is figure 7.28. And this is figure 7.28 main.java. So here's the code for it, and we'll see, we'll take a look at this code in a bit. The main part of the code is down here with this action performed. So you're used to doing these action performed, implementing this action performed in those previous Java programs, right? So, there's actually one other thing I wanted to demo. I don't know if you noticed, but you see this complex, this kind of complicated comment section. Well, this follows the standard. There's this thing called JavaDoc that I didn't describe in the book. But look, if you come down here and you right-click on this and you say Generate JavaDoc, watch this. This is so cool. Boom. Look at this HTML documentation that gets generated automatically by that JavaDoc. It goes through and it actually analyzes all the classes in your programs and figures out the links in between them and gives you and automatically shows you all that. See, here's all the information. See, look, figure 7.28 of blah, 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 computer systems, blah, blah, blah. So you can document, it puts this all in this HTML file, in this HTML. So, see, like here's the you know how that's file codes, code, you know, so you can do HTML and document your stuff. So anyway, that's I encourage you to use JavaDoc, this JavaDoc documentation, and see, because it's a pretty big industry standard. Anyway, but without further ado, let's just go ahead and run this, and so that we can see how it works. So we'll do run. Now see, here's our dialog box, figure 7.28. Enter a string of letters and digits. Now do you remember what this is going to recognize as an identifier? So do you remember when we did CAB3, C-A-B-3? Remember that? So watch this. Let's parse this. Click. And boom, what did it say? CAB3 is a valid identifier. And here, let's try, what was that example that we did the other day? 23 skidoo. I don't know how to spell skidoo. Parse. 23 is not a valid identifier. All right? So it tokenizes. Does everybody see what it did? So that's the demo. Okay, so that was the demo. And what I want to show you right now is the way that program worked is it was a table lookup implementation. So here, the finite state machine implementation techniques, there's two primary ways to do it. And by the way, this is a general software engineering design decision that you have to make. And frequently in software engineering, there's two different ways to accomplish your computation. One of which is based on table lookup, and another which is based on direct code. So even though this is, we have these two different ways to do this with finite state machines, you also have these two different ways to do this in lots of computation. So it's a good general software engineering principle to know the difference, how to approach a computation problem. And so we're gonna look at both of them, see how they work. So the first one we're gonna look at is table lookup. So here's a table lookup implementation. Now look, do you remember in figure 7.12? This was the state transition table. Do you remember this? Of that finite state machine that recognized an identifier. So we had states A and B and C, and then the next state, you know, we went from A to B on a letter, and we went to A to C on a digit. Remember that? So here's the table in figure 7.12. So what we're going to do is we're going to put this table right in the program, and we're going to use it. So here in figure 7.28 is a slide of what we just demoed, and here's that JavaDoc stuff, figure 7.28. There's the JavaDoc that we looked at, and I'm going to skip over these this code to generate the dialog box. And so here, what do we have here in figure 7.28, this part of the figure? First of all, we have public static Boolean is alpha. Now what does static mean in Java?
Can be changed.
No? One per what instead of one per what?
Oh.
Now, one per what instead of one per what? One per class instead of one per object. Okay? So public means public access, static means one per class. So, and then Boolean, so this returns Boolean, and is alpha. Now, does everybody see the code for is alpha? Char, ch? It returns, so we have to be able to detect whether or not it's a character, right? And then now look at what we have for the states. Now what is static final int s underscore a equals what? 0. Static final, so what does static mean? One per class instead of one per object. And what does final, now what does final mean? Now what does final mean? Yeah, that's constant. That's where you can't change it. In Java, that's Java terminology. Now are we good for this? So this is const. This is the way you do const in Java. Are we good? So static final int, so state A, state B, state C. State A is 0, state B is 1, state C is 2, and never will there ever be anything different. right? So it's not a variable, it's a constant. And now what do we have for alphabet? We have static final int what? T letter is what? 0, and T digit is what? 1. So we're defining these as constant integers, these things, right? And now look, what do we have? State transition table. Static final int, now what is that? Square bracket, square bracket?
Is it like an array?
It's a two-dimensional array. Does everybody see that? It's a two-dimensional array. And what do we call our static final int two-dimensional array? We call it FSM for finite state machine. And do you see this Java terminology, how you can initialize a two-dimensional array? It's an open brace at the top and a closed brace at the bottom, and then a what? Open brace and closed brace for each what? Row. So do you see that this is that table? This is our state transition table. What is it we have? What do we have in the table? BC, BB, CC. Let's go back here. BC, BB, CC in figure 7.12. Does everybody see that that's that table? Are you with me? Is everybody good? Now watch this, you guys. Look how short this is. This is the code that does it. Look what we have for action performed when you click the button. So first we do string line gets what? Text field dot get text, and then char ch. So ch is an individual character, and we have. Well, I see what's happening now is we have it's the end of it's time to go. So anyway. But look how short this is, and unfortunately it's time to go now, so we'll start with this on Thursday. You do have, your problem for Thursday is to actually modify this, and it will still be due on Thursday. Well, we can make it Friday if you want, but it's Friday before spring break, but anyway. So we'll start right here at the beginning of class on Thursday. All right, good deal. See you next time.